Hey everyone, thanks for opening up your Science Sketchbook. In this video, I'll be going through 5 must-know peaks for IR spectroscopy in organic chemistry. Stay until the end for a little challenge problem for you to try. So, super briefly, let's talk about what infrared spectroscopy is. IR spec shows a range of wavelengths of infrared radiation that molecules absorb. This is associated with types of vibrations among the atoms and bonds. Kinda sounds a little abstract, but the basic idea for Organic Chem 1 is that an IR spectrum will show you what functional groups are in a molecule. It can also show you some information about the different hybridizations present, like sp3 or sp2 atoms. See those examples in the pictures. The x-axis will be the wave number that indicates a particular functional group. The y-axis has the absorbance, where the shapes and appearance of the peaks there will help you recognize the group as well. So I'm going to simplify 5 major absorbances in an IR spectrum and how to tell apart the small differences. We will cover 1. Carbonyls, so those are CO double bonds. Keep in mind that there are many functional groups that have a carbonyl in them, but I'll show you how to tell the difference between a couple of them. 2. Hydroxyls, so those are oxygen-hydrogen bonds, and those can be present in a variety of functional groups as well. For example, we'll look at the difference between an OH in a carboxylic acid versus one in an alcohol. 3. Alkynes, so those are carbon-carbon triple bonds, and we'll look at the difference between internal and terminal alkynes in the IR spectrum. 4. Amines, and specifically we're talking about primary and secondary amines, so the nitrogens that have hydrogens on them. And finally, not exactly a functional group, but just simple sp3 carbon-hydrogen bonds. Although there are many molecules that have this, hydrocarbons in general, right? It sometimes comes down to just that fine difference. This peak is pretty common across different IR spectra, so may as well know it. For the class that I teach, these 5 must-know categories usually narrow down your answer pretty well. Keep in mind that different IR absorbances usually have a range to look through, but I'm going to give it as one solid value to look around so that it's easier for you to study and remember. Well, let's begin with carbonyls. To recognize this group, you'll look for a strong, sharp peak around the 1700 range. Take a look at this spectrum. This is a sharp peak, and it is indeed located at about 1700. So if you see that peak, it can be a carbonyl from any of your carbonyl functional groups. Think carboxylic acids, amides, aldehydes, ketones, esters, things like that. Here's the full IR spectrum for this real molecule example. So that ketone gives that sharp peak there. Note that there's going to be a lot of mess around the signal of interest or other groups to determine, but you'll be able to hone in on the group you need to identify the molecule. Next, we have hydroxyl groups, so an oxygen-hydrogen bond of some sort. This will give a distinct broad band with a range on or above about 3000. I'm going to give you 2 ways you may see this group. Notice, we have this one above that is shifted more to the left of 3000, and this one below centered on 3000. These differences indicate the OH group of 2 different functional groups. The one on top indicated the OH of an alcohol specifically, so think of an OH bonded to its own carbon. The one below indicates the OH of a carboxylic acid, so think of an OH that is bonded to a carbonyl carbon. Thus, these different signals show slightly varied absorbances. This is the full IR spectrum for the molecule here, a form of glucose. There is indeed alcohol present. And this is the full IR spectrum for the carboxylic acid example, specifically acetic acid. So those OH hydroxyl groups give these broad bands in this range. Just keep in mind, for alcohol, it's shifted to the left and generally kind of smoother looking too, while carboxylic acids are centered on that 3000 mark, and generally a bit more scratchy looking. And perfect example here to keep you reminded, look at the IR spectrum for the carboxylic acid on the bottom. Do you recognize another peak? Yeah, that sharp one at 1700 for that carbonyl group. It happened to be a part of this molecule, and since it had that broad band on 3000, we knew that specific carbonyl would be a carboxylic acid. Alrighty, next we have alkynes, or carbon-carbon triple bonds. All alkynes have a weak peak around 2100. See that pretty small peak? That means there is some kind of alkyne here. It could be an internal one, where there's carbons continuing to either side of the triple bond, or it could be a terminal one, where it's just pretty much at the end of the chain. To know if it's terminal, you'll also have a bonus peak, a strong peak around 3300, like shown. So if both of these peaks are shown, it is a terminal alkyne. If just the weak peak is there, that means there's an internal alkyne. Let's see the full spectrum. This example molecule is propyne, or 1-propyne specifically. Notice that the triple bond is at the end of the carbon chain. That means it's terminal, so it has both of these peaks. Here's something to compare. We have 2-pentyne here. It has a triple bond internally, not at the edge of the chain. Therefore, it would not give this spectrum because it should only have the weak peak, not this further one in 3300. That bonus is solely reserved for terminal alkynes. Well, next we have amines. These produce a medium peak in the 3400 region. Note, this is only for amines that have hydrogens on them. A primary amine has 2 hydrogens, as in NH2. This means it'll give a double peak in this region. A secondary amine has 1 hydrogen, as in NH. This will give a single peak in this region. If it was a tertiary amine, which is just N, it would not show a signal in this region. So, look at the chart. Do you think this is a molecule with a primary amine or a secondary amine? Yeah, a primary. Remember, primary means 2 hydrogens. I know it can get a little confusing there, because secondary is 1, sounds kind of switched, but keep it in mind, this is an NH2 group bonded to the rest of the molecule. So, with the rest of the spectrum in view, we can see the actual peaks for this primary amine, specifically aniline. Again, there's a lot going on with this graph, but if you can recognize those peaks there, you're a step closer to being able to quickly recognizing molecules from an IR spectrum. And again, if there was only one medium peak in the region highlighted, you'd have only 1 hydrogen on that amine. All right, finally, we have the last kind of significant signal. It's not really a functional group again, but you may have noticed it in the various spectra I just went through, because once again, it's pretty common. Look at this spectrum. The peak is pretty strong here, and it is literally bordering 3000, so I kind of left it at 2990. This peak can be a little shorter or wider, but this is the general idea. Here's the full spectrum. I just reused the ketone one from earlier. It definitely has single-bonded carbons that have hydrogens on them, so it would give this sp3 peak. If you're having trouble seeing those hydrogens, take a look at them all here. And yeah, look, it's got plenty of options. It just needs at least one to give that absorbance. Alrighty, so those were some major peaks in organic chemistry. If you know at least those 5 types, you're bound to narrow your answer down pretty well. So just keep in mind, I gave a simplified wave number for each, but of course any of these peaks can fall within a range. I just find it easier to generalize that range to make it easier to study. And of course, you can always consult an IR table, which will tell you some ranges to check out for other functional groups if you need more detail in your spectrum. Now, to recap, why don't you help me out and test your memory? Help me label the 5 major IR signals with the general wave number you'd find them at, and the general appearance of those peaks. This is helpful practice in case you get IR spec questions that are written instead of graphical. Feel free to pause the video here if you need some time. Did you remember them all? Awesome job. So carbonyls are at 1700 and they are sharp, strong peaks. Hydroxyl groups kind of extend on or about the 3000 range and they look like broad bands. Alkynes all have a weak peak in 2100, and if they're terminal, they have a bonus peak, a strong peak, in 3300. Amines are found in the 3400 range, and the number of medium peaks present correlates to the number of hydrogens on that amine. Finally, sp3 carbon-hydrogen bonds are found at around 2990, basically right before 3000, and you would see them as a medium or strong peak. So let's do one quick practice problem before we head out. So, which molecule matches this IR spectrum? Sketch suggests you pause here to try on your own. Alright, let's see. It's not this first one, right? This spectrum shows a broad stretch kind of to the left of 3000 and kind of smooth looking, right? With a carboxylic acid, it should be centered on 3000 like this and kind of rough looking. So what was given was probably the OH of an alcohol, not a carboxylic acid. It's not the last one either. I see that there is that OH alcohol peak, and it has that carbonyl peak in 1700, but look at all the carbons. None of them are sp3, so you wouldn't have this peak right here. If you decided to consult an IR key for a little more detail, you'd also notice that sp2-CH bonds would produce a weak peak a little past 3000, and there would also be another peak around 1600. Neither of those peaks are present as well, so however you solved it, that means the middle one, 4-hydroxy-2-pentanone, is the correct answer. We have the broad OH band of just an alcohol, perfect as this OH group is not on the carbonyl carbon like the first one, right? We have the sharp carbonyl peak in 1700, which works with that ketone, and we have the peak of the sp3-CH bonds since there are indeed single bonded carbons here. If you got it right, amazing job, I'm super impressed. If not, that is okay. You can totally review the charts in this video again or look up more graphs to practice. And with that, great job working through your science sketchbook today. If this video helped, feel free to drop a like, and if you'd like more related content, feel free to check out my channel and subscribe. Alright, that's it for now. Bye!